Last night, I watched this video on YouTube about how special relativity makes magnets work. And this was a question that had been in my head for a very, very long time, and I'm glad that I finally saw it answered. And for a long time, I've had this conjecture, basically, that magnetism doesn't really exist, but it is electricity observed from another reference frame. Now, what this video did seems to kind of confirm that conjecture. Now, I've never been able to quantify what should happen if these two things are not just equivalent but the same. I've just recalled I usually say this conjecture: magnetic fields are not caused by changing E fields. Rather, magnetic fields are changing E fields. So what this video did gave me a way of quantifying this by considering basically a simple application where we have a wire containing positive charges and negative charges. And what we're going to do is send a current through that wire. And when we send that current through the wire, we see the negative charges start to move. So these negative charges will move to the left, but technically we call that a current to the right, and that should generate a magnetic field going around the wire. The way that magnetic field is described is generally, I would point my right thumb this way. Let's see if I can draw a picture of a hand. Okay, that's a little bit of an odd hand, but what is going on there? Fingernails on it. The magnetic field goes around the wire in the direction of my fingers around my right hand. So I'll draw the magnetic field like the pointy tips of arrows coming out of this side. So this is the magnetic field coming out of the image. Now, now presumably, if I put a positive charge in here, I'll make that red. Let me actually just put it right here. It should not be affected by those magnetic fields at all. But if I have that charge move inside the magnetic field, it actually will be affected by a force which is related to the cross product of the velocity of the charge and the magnetic field of the charge. Now I have to twist my right hand around to do this one. Basically, you would point your fingers in the direction of the velocity and then point your fingers in the direction of the magnetic field, and then the force should be this vector here. So that charge, if I'm thinking about this correctly, should be attracted to the wire. Now, why is that? From the special relativity explanation, the positive charges are Lorentz contracted, and the negative charges, which are moving even faster relative to the positive charge, are Lorentz contracted even more, which would mean that the negative charges have higher density, and so since the negative charges have higher density in the positive charge's new perspective, it's actually that higher charge density of negative than positive that will create the magnetic force that pulls them in. Now I'll admit I was confused for a moment, because the example that was given by Veritasium simply used a different velocity here. Instead of having this object moving in the opposite direction, he had the positive charge just match speed with the drift velocity of the electrons. in which case the negative charges ended up being uncontracted while the positive charges ended up being contracted. And what would happen then is that the positive charges look denser, and that would cause the positive charge to push away. So if we reverse this, in fact, it would still be mathematically equivalent to this, but your velocity vector would point that way, your magnetic field that way, and then you'd have your force going that way. Now what I'd like to do in this video is to at least start a more detailed analysis, which question, can I derive the force equals QV cross B from the Lorentz contraction equations? So the first thing I want is an explicit form for the equation for the Lorentz contraction. And here it is, L equals L sub naught over gamma. And what else do I need? I think I need the charge density or the carrier density of the wire. Let's say for a second, I've just for the sake of argument, we just need to concern ourselves with one kind of charge carrier. We'll make them positive charge carriers just to fit the sign conventions. I may or may not need to concern myself with the cross-sectional area right in here. I do want to be concerned with the current and what's called the drift velocity of so I'll need to find the drift velocity of the electrons. Oh, and I want to make one other change. I've been talking about the magnetic field force being QV cross B, but the magnetic field, I believe, is Li cross... that doesn't look quite right. I believe it goes force equals Li cross B. This is the magnetic force on a current carrying wire. But that's not what I'm looking for. I'm looking for the magnetic field from a current carrying wire. And here I find a example of it from hyperphysics. So here it is, magnetic field mu sub naught I over 2 pi r. Seeing the electric permeability, or the magnetic permeability in there, probably suggests that I'm going to want something involving epsilon naught, which is the electrical permittivity of free space. So I'm going to put those two things together. I know I have this memorized, that the speed of light is equal to 1 over the square root of mu sub naught epsilon naught. So we'll probably want to use that relationship in here somewhere. And we're also going to want the electric field from the current carrying wire. And actually I'm going to just call it a long cylinder of charge. How about this one? Electric field from a cylinder infinitely long. And this is one of Gauss's standard problems. And this equation also I can find on hyperphysics. So the electric field is equal to the linear charge density divided by 2 pi r epsilon naught, and r is just how far you are away from the center of the cylinder, or the distance from the wire. Another thing that I want to get is the drift velocity, which is the average velocity of a particle such as an electron attains due to an electric field. This is something that I want to involve in our equation, but it might cancel out at the end. This looks like a good expression of it for our purposes, that the drift velocity is proportional to, or is equal to, the current in the material divided by the number of charge carrier density times the area, cross-sectional area, and Q is the charge on the charge carrier. So what are the units on these things? Current would be coulombs per second. If N is particles per meter cubed, and the area is in meters squared, and Q is in coulombs, does this cancel out and give us a velocity? So coulombs cancels out with coulombs. Meters cubed cancel out with meters squared and goes up to the top. So we have meters on the top and we have seconds on the bottom. So this would give us a velocity. Now I believe I've gathered up all the pieces to the puzzle. It's just a matter of putting them together now. So my big question is B equal to E. And more explicitly, I want to know if the force caused by this magnetic field is equal to the force caused by this electric field. And the force caused by the magnetic field is QV cross B. The force caused by the electric field is just force equals QE. So essentially it's this part. Is V cross B the same as the E field from the Lorentz contracted charge density? And the key is that lambda is basically N divided by L, and L is L sub naught divided by the square root of 1 minus V over C squared. But there's going to be two different velocities in here. One is going to be V, I'll call it V plus. It's the relative velocity with the positive charges, and I'll put another V minus, which is the relative velocity with the negative charges. And then we can find the difference between V plus and V minus based on this drift velocity equation here. Now I'm going to try to put all these things together in the next video. I can already see potentially this N, which is the number of charge carriers, may cancel out, because here we have an N and here we have an N. And we want that to cancel out because the final value is going to be based on the current, not the there's no number of charge carriers in our equations for the force and magnetic field on the wire. And if these calculations turn out, then I'll have really my first genuinely intuitive sense of the phenomenon of magnetism and how it works. And what I'm hoping is that this eventually leads to a deeper understanding of how electromagnetic waves propagate through space.